Now let us study parametric statistical tests for different samples. Okay, so before starting this, suppose we wish to measure teaching aptitude of MA Psychology students. Okay, so that will be a large sample, okay, by using a verbal aptitude teaching test. Now, it is not possible and also not convenient to measure the teaching aptitude of all the enrolled MA Psychology student trainees. Okay, and hence we must usually be satisfied with a sample which is drawn from the population. Okay, however, this sample should be as large as randomly drawn as possible so that it represents adequately all the MA Psychology students of IGNOU. So sample should be a representative sample so that it represents all types of MA Psychology students. Now, if we select a large number of random samples of 100 trainees, suppose, okay, each from the population of all trainees, then the mean values of teaching aptitude scores for all samples will not be identical. Okay, so you select a large number of random samples of 100 trainees each. Okay, and you calculate the mean values of each of the sample, then that mean values will not be identical. So, like a few will be relatively high, a few will be relatively low, but most of them would tend to cluster up around the population mean. Okay, now the sample means due to sampling errors will not vary from sample to sample. Okay, will not, but will also usually deviate from the sample mean. So the sampling means due to sample errors, they will also vary. Okay, they will vary from sample to sample and will also deviate from the population mean. Each of these sample means can be treated as a single observation and these means can be put in a frequency distribution which is known as the sampling distribution of the means. Okay, so sampling distribution of the means is basically the sampling distribution of the mean means for each sample you will get a certain value. So if you are drawing like 100 samples, for each sample you will get a mean value like x1 bar for sample 1, x2 bar for sample 2, x3 bar for sample 3 and so on, x 100 bar for 100 sample. Each will have a distribution. Okay, like this, how many times this mean value has occurred, how many times this mean value has occurred, how many times this mean value has occurred out of the total values. Okay, so you will have a certain type of a distribution of these sample values of different means. So this is called a sampling distribution. Okay, so what is a sampling distribution? Is basically the distribution of the sample. So you will get actually the frequency of each sample mean. How many times this sample mean is occurred, how many times this sample mean is occurred, how many times this sample mean is occurred up to this. Okay, how many times this sample mean is occurred. So it will give you a sort of distribution, okay, of the mean, the sample mean. So that is known as sampling distribution of the mean. Okay, so for that an important principle is there which is known as central limit theorem. Okay, so it's what does the central limit theorem do? It describes the characteristics of sample means. Okay, according to this theorem, if you take a large number of equally sized sample greater than 30 in size, okay, the size of the sample is greater than 30, selected at random from the infinite population. So if there is a big infinite population, and from that you select a large number of samples of equal size, and the size of each sample is greater than 30, then the means of the sample will be normally distributed. Okay, so this is one of the results of the central limit theorem. The means of the sample will be normally distributed and the average value of the sample mean will be same as the mean of the population. This is another result of the central limit theorem. Okay, and so these are the two main results of the central limit theorem. This is the first result and this is the second result. Okay, then the distribution of sample means will have its own standard deviation. Okay, so whatever the distribution of sample means it will be, it will have its own standard deviation. This standard deviation is known as standard error of mean, which is in short form denoted as SEM or sigma of m. Okay, this is known as standard error of mean. Okay, and so this error of mean, it basically gives us a clue as to how far such sample means may be expected to deviate from the population mean. Okay, so the formula for the standard error of mean is denoted by sigma m and is given by sigma by root n. Okay, where sigma is the standard deviation of the population and n is the size of the sample. Okay, so this is about the central limit theorem. Then let us discuss what is parametric statistical measures for calculating difference between means. Okay, so basically what happens that in some research situations, we require the use of statistical technique to determine whether a true difference exists between the population parameters of two samples. Okay, the parameters may be mean, standard deviation, correlations, etc. Okay, so for example, if we see that, for example, suppose we wish to determine whether the population of male MA Psychology students enrolled with IGNOU, it differs from their female counterparts in their attitude towards teaching. Now, in this case, we would first draw samples of male and female MA Psychology students. Next, what we will do? Okay, so first we will draw the sample. Next, what we will do? We will administer an attitude scale measuring attitudes towards teaching on the selected samples, compute the means of the two samples, and then find the difference between them. Okay, so let the mean of male sample be, let the mean of male sample be 55 and that of female sample, okay, that is 59. Okay, then it has to be a certain if the difference of how much difference is there? 4. A 4 between the sample means is large enough to be taken as real, okay, and not only due to sampling error or chance. Okay, so what you have to do in order to test the significance of the obtained difference of 4, we first need to find out the standard error of mean, standard error of the difference of the two means. Okay, why? Because it is reasonable to expect that the difference between two means will be subject to some sampling errors. Okay, then from the difference between the sample means and standard error, we can determine whether a difference probably exists between the population mean. Okay, so how in the next sections we'll study how to study the significance of the difference between means of two independent large and small samples. Okay, now let us study the significance of the difference between means, the difference between means of two independent large samples. Okay, so basically means are said to be independent or uncorrelated when computed from samples drawn at random from totally different and unrelated groups. So let us see for large samples. So this is in basically you have learned that the frequency distribution of large sample means drawn from the same population. Okay, they fall into a normal distribution around the population mean as a measure of central tendency. Okay, it is reasonable to expect that the frequency distribution of the difference between the means computed from the samples drawn from two different populations will also tend to normal, okay, with a mean of 0 and standard deviation, which is called the standard error of the difference of means. Okay, so the standard error, the difference of mean is denoted by sigma dm, which is estimated from the standard errors of two sample means sigma m1 and sigma m2. The formula is sigma dm is equal to under root of sigma m1 plus sigma m2, in which sigma m1 is standard error of the mean of the first sample and sigma m2 is the standard error of mean of the second sample. Okay, n1 is the number of cases in the first sample and n2 is the number of cases in the second sample. Okay, now let us see the significance of the difference between the means of two difference between the means of two dependent samples. Okay, so basically two correlated means, or we can also say the difference between the means of two dependent samples. The two samples are dependent, then the means will be correlated. Okay, so means are basically said to be dependent or correlated when obtained from the scores of the same test, okay, administered to the same sample upon two occasions, or when the same test is administered to equivalent samples in which the members of the group have been matched from person to person. Okay, so this is the standard. So this is the standard error of mean, or difference between two correlated mean, is denoted by sigma d. Okay, so sigma d is given by this value. Okay, so if two means are correlated, then how to calculate the difference between standard error of the difference between two means? Okay, so here M1 and M2 are means of the scores of, suppose, initial and final testing. Okay, and here sigma M1 is the standard error of initial test mean, and sigma M2 is the standard error of the final test mean. Okay, and R12 is the correlation between the scores of initial and final testing. Okay, so there are some scores on what some initial testing has been done, and there are some scores again in which final testing has been done. So M1 is the score of the mean score of initial testing, and M2 is the mean score of final testing. Sigma M1 is the standard error of initial test mean, and sigma M2 is the standard error of final test mean. Okay, now suppose you want to calculate the standard error of the difference. Okay, so this is the standard error of difference, or sigma d. It is given by this formula. Okay, so you have to remember these formulas. Now, so let us study the significance of the difference between the means of three or more samples when the samples are greater than three or more, or greater than two. Okay, so basically, so suppose we have n greater than two random samples, and we want to determine whether there are any significant differences among their means. Then what we have to do for this, we have to use an F test. Okay, so we have to use an F test and compute an F value, that is analysis of variance. So when we want to study the difference between means, like if there are different groups, more than two groups, okay, like there are suppose n groups. So mean of this is group is mu1, mean of this group is mu2, mean of this group is mu3, and suppose mean of this group is mu1. And we want to study the significance of difference between these means, then we will use analysis of variance technique, and from that and we'll also use an F test. Okay, and we will use the F statistic, okay, to study whether that this difference is significant or not. Okay, so basically, so analysis of variance has some following basic assumptions underlying it, which should be fulfilled in the use of this technique. So there are some basic assumptions which should be fulfilled for use of analysis of variance. The first is the population distribution should be normal. Okay, this assumption is, however, not specially important, but it should be normal. Then Eden and Yates, they were some scientists, they showed that even with the population departing considerably from normality, the effectiveness of the normal distribution is still held. Okay, and the other assumption is that all the groups of certain criterion or of the combination of more than one criterion should be randomly chosen from the subpopulation having the same criterion or having the same combination of more than one criterion. These are some assumptions we need to be satisfied in case of analysis of variance. And the subgroups under investigation should have the same variability. So the assumption is tested by applying Fmax test. What is the Fmax test? It is given by largest variance divided by the smallest variance. Okay, so in analysis of variance, we usually have three or more groups. That is, there will be three or more variances. Okay, unless the computed value of Fmax equals to or exceeds the appropriate F critical value at 0.05 level. So this is in any statistic books, there is an appendix there is an F table. Okay, so you can see the F table of the appendix of any statistical book. Okay, and then you can check. I'm not going into the detail of F test because it is not mentioned in your syllabus. I'm just giving you an introduction. So in that you can find the F critical value, and if F max exceeds the appropriate F critical value at 0.05 level in the table of the appendix, then it is assumed that the variances are homogeneous and the differences not significant. Okay, so on that basis of that you can accept or reject your null hypothesis based on the F value. Okay, before we move further, there is a small correction here. So in this formula, it is sigma square m1 plus sigma square m2. Okay, so sigma dm, here it is sigma square of m1 plus sigma square of m2. Rest all the things are same. Okay, so this was the small correction. Okay, please note. So basically, how do you do the testing of the significance of difference in means? So you use the F test. Okay, and unless the computed value of F max equals or exceeds the appropriate F critical value at 0.05 level, then it is assumed that the variance are homogeneous and the difference is not significant. Okay, so suppose this is your graph. Okay, so suppose this is the F critical value and your calculated value exceeds this critical value, then you are going to reject your null hypothesis and you will say that the differences are significant. Otherwise, unless this happens, okay, that is your F max is equal to or greater than critical value, then the differences is significant. Okay, otherwise the difference is not significant. Okay, so unless the computed value of F max exceeds equals to or exceeds the appropriate F critical value at 0.05 level, it is assumed that the variances are homogeneous and the difference is not significant. Okay, so what is hypothesis testing and all that you'll study later. Okay, but for now you have to remember this, that we use this F max test. Okay, and in the analysis of variance technique to understand whether the difference in mean is significant or not. Okay. Now, let us study this parametric statistics measure related to the Pearson R. Now, the sampling distribution of R is not normal except when the population of R is near 0 and the size of the sample is large, that is n is equals to 30 or greater. Okay. When R is high, that is 0.80 or more, and n is small, the sampling distribution of R is skewed. Okay, and it is also true when R is low. So what is R here? So basically the mathematical basis for standard error of a Pearson's coefficient of correlation is R. Okay. So the sampling distribution of R or the Pearson correlation coefficient is not normal. Okay, except when the population of R is near 0 and the sample size of the sample is large. When the correlation coefficient is very high and n is small, then the sampling distribution of R is skewed. Okay, and it is also true when R is low. Okay, now let us study the non-parametric test used for inferences. Now we'll study some of the non-parametric tests used for inference. So the most frequently used non-parametric test for drawing statistical inferences in case of unrelated or independent samples are: first is chi-square test, second is median test, and third is the Mann-Whitney U test. So let us study the chi-square test. So first of all, the chi-square test is applied only to the discrete data. Okay, the data that are counted rather than measured. It is a test of independence and is used to estimate the likelihood that some factor other than chance account for the observed relationship. The chi-square test merely evaluates the probability that the observed relationship results from chance. The basic assumption, as in the case of other statistical significance, is that the sample observations have been randomly selected. Okay, so here, this is the formula for the chi-square test. So it is written as, first of all, chi-square is denoted by this. Okay, so chi-square C, that is equal to summation OI minus EI whole square divided by EI. That C is the degrees of freedom, O is the observed value, and E is the expected value. So you for now you have to remember these formulas. Okay. And this formula for chi-square can also be, so here it is chi-square. It can also be written as chi-square is equals to summation of f naught minus fe, okay, whole square divided by fe. Okay. Same thing as here. Instead of oi it is written as f naught, and instead of ei it is written as fe. So f naught is the frequency of occurrence of observed or experimentally determined fact, and fe is the expected frequency of occurrence. So this is the formula. We just have to remember this formula. Then let us study the median test. The median test is used for testing whether two independent samples differ in central tendencies. Okay, it gives information as to whether it is likely that two independent samples have been drawn from the population with the same median. Okay, and it is particularly useful when even the measurements for the two samples are expressed in an ordinal scale. Okay, so in using a median test, we first calculate the combined median for all measures, that scores in both the samples. Then both set of scores at the combined median are dichotomized. Okay, dichotomized means divided into two categories, and the data are set in a 2x2 table with one row containing rows below the median and other row containing above median. Okay, on the column side we have two columns, one containing the sample 1 and the other containing the sample 2. Okay, so for now you just remembered what is this median test. It is basically used for testing whether two independent samples they differ in their central tendency. Okay, so basically it gives the information as to whether it is likely that two independent samples have been drawn from populations which has the same median. Okay, so just please remember this much for your median. This is the small description of how this median test is conducted. Then there is also a test known as the Mann-Whitney U test. The Mann-Whitney U test. What happens in this Mann-Whitney U test? The Mann-Whitney U test is more useful than the median test. Okay, and it is one of the most useful alternative to the parametric t-test when the parametric assumptions cannot be met, and when the measurements are expressed in the ordinal scale value. So it is basically a more useful test than the median test, and it is a useful alternative to parametric t-test. Okay, when the parametric assumptions cannot be met, and when the measurements are expressed in ordinal scale value. Okay, now let us study some non-parametric tests for related samples. Okay, so basically various tests are used in drawing statistical inferences in case of related samples. Okay, then in this section we will study the sign test, and we'll see some other tests also like Wilcoxon matched pair sign ranks. So the sign test is basically the simplest test of significance in the category of non-parametric tests. It makes use of plus and minus signs rather than quantitative measures as its data. It is particularly useful in situations in which quantitative measurement is impossible or inconvenient. But on the basis of superior or inferior performance, it is possible to rank with respect to each other the two members of each pair. Okay, so basically it uses plus and minus signs. Just okay, and the sign test is used either in the case of single sample from which observations are obtained under two experimental conditions, and the researcher wants to establish that the two conditions are different. Okay, so for this sign test is used. And the use of this test basically does not make any assumption about the form of the distribution of differences. And the only assumption underlying this test is that the variable under investigation has a continuous distribution. This was about the sign test. And then the Wilcoxon matched pair signed rank test. So basically the Wilcoxon matched pair signed rank test is more powerful than the sign test because it tests not only the direction but also the magnitude of differences within the pairs of matched groups. Okay, so this test, unlike the sign test, it deals with the dependent groups made up of matched pairs of individuals. Okay, and it is not applicable to independent groups. The null hypothesis would assume that the direction and magnitude of the pair difference would be about the same. Okay, so this was some of the tests for the so these were the some of the tests about non-parametric tests for the related samples. Okay, so so this was about your unit. So basically, what we did in this unit, we just gave an introduction to parametric and non-parametric statistics. Okay, so we studied some terms related to parametric and non-parametric statistics. We did not go into details of each of the tests, that how those tests is done, what are the examples, because this was just an introduction to what is parametric statistics, what is non-parametric statistics, what is the difference between parametric and non-parametric statistics, and then we basically focus on describing the nature and meaning of parametric and non-parametric statistics. Okay, so we also studied the assumptions of parametric and non-parametric statistics and advantages and disadvantages of parametric and non-parametric statistics. So basically, this unit was a sort of like a little bit of more theoretical about parametric and non-parametric statistics. We just studied some definitions and some assumptions, advantages and disadvantages. We studied just what are the different types of tests. We did not go into detail of each of these tests. It was just an introduction. As to you should know basically out of this unit that what are the different types of what is a parametric statistic, what are parametric statistics, what are non-parametric statistics, what are the tests, and what are the advantages, disadvantages, and what are the assumptions. And before concluding the unit, I just want to discuss something more here. So here in parametric statistics, measures related to Pearson's R. So if you want to study a sound method for making the inference regarding Pearson's R, especially when its magnitude is very high or very low. Okay, it's very high or very low. Okay, then you can convert it R into Fisher's Z coefficient using conversion table. Okay, you can see any standard statistics book for the reference. Okay, so to convert R into Fisher's Z coefficient, you can use a conversion table provided in statistics book. Okay, and you can find the standard error of Z. Okay, the sampling distribution of Z coefficient is normal regardless of the size of the sample N and the size of the population R. And furthermore, the standard error of Z depends only upon the size of sample N. Okay, and the method of determining the standard error of the difference between Pearson's coefficient of correlation of two samples is first to convert the R's into Fisher's Z coefficient and then to determine the significance of the difference between the two Z's. Okay, so if you want to study this, you can see and study your any advanced statistics books. Okay, for now you have to remember this much. And okay, this concludes your unit. And these are some previous year questions in which you have to describe parametric and non-parametric statistics, and you have to describe the assumptions of parametric statistics. Then you have to explain non-parametric statistics with a focus on its assumptions, advantages, and disadvantages. And then you have to write short notes on man-with-me interest. So this pretty much concludes your unit. Please study this unit well. Okay, and all the best to all.